We discussed theorem 15 at the end of the last video. I should mention that applies assuming that the function that we have is differentiable at the point p naught, but it gave us some important information about the gradient, the significance of both its magnitude and its direction. So here's a point p naught, here's my gradient of f at p naught. Now I've drawn it as if it's not zero. Theorem 15 is actually true even if the gradient is zero, it's just incredibly boring. Because of course if the gradient is zero, then because the directional derivative is just the dot product of the gradient with the unit vector, if the gradient is zero, all directional derivatives are zero. That's your max, that's your min, you get them in all directions. Okay, but it's more interesting if the gradient is non-zero. So if we hold fixed our point p naught, and we're working with this function f, so if we're not varying the point, the gradient at that point is a fixed vector. What we're going to vary is the direction of our unit vector. Okay. And of course, as we vary that, that changes the angle theta that u makes with the gradient. Okay. Now, because the directional derivative is this dot product, and the dot product is just the magnitude times cosine of theta, notice this magnitude, the magnitude of u, is just 1. So what we get is that the value of the directional derivative is the magnitude of the gradient at p naught times cosine theta. And we said that that's going to be maximized. So duf at p naught is maximized, well, when theta is equal to 0, because that's going to make cosine of theta equal 1, and that's the only angle between 0 and pi, which is the range that theta is allowed to take on, that has a cosine of 1. So it's maximized when theta is equal to 0, making cosine of theta 1. Of course, what that means is that u would be pointing in the same direction as the gradient. Not just parallel to it, but parallel and in the same direction. Okay. That's important because, of course, if we're pointing in the opposite direction, that would make theta equal pi. So it's going to be minimized when theta is equal to pi. So that would be when u is parallel to the gradient but pointing in the opposite direction. And I say minimized, but that's going to actually mean that it's at its most negative value. So it's not that it's increasing the most slowly, it's that it's decreasing the quickest when we're pointing in the direction opposite the gradient. Okay. And the maximum value is, since if theta is 0, cosine of theta is 1, the maximum value is just the magnitude of the gradient of f at p naught. And the minimum value, which again might be more helpful to think of that as the most negative value, the fastest rate at which my function is decreasing, and that's just going to be negative 1 times this magnitude. Okay, so that's kind of interesting. That establishes, let me here draw in the opposite of the gradient. So if we're going in this direction, our directional derivative is maximized. If we're going in the opposite direction, the directional derivative is minimized. And somewhere in between, it takes on its intermediate values. I can actually see if theta is an acute angle, I'm going to have a positive directional derivative. As soon as theta becomes an obtuse angle, so I'm making an obtuse angle with the gradient, we're going to have a negative directional derivative. But right where that changes, kind of interesting. If theta were pi over 2, so that u was perpendicular to the gradient, again, assuming that the gradient is non-zero, because that's the interesting case. Okay. If that's the case, then cosine of theta would be 0, and my directional derivative would be 0. But I want to think about another way that I could get a derivative of 0, because I have a derivative of 0 when I'm constant. And if I'm talking about a function of two variables is constant on its level curves. A function of three variables would be constant on its level surfaces. So this sort of suggests a relationship between the gradient and the level curves or the level surfaces, depending on whether it's a function of 2 or 3 variables, of our function. So let's take a look at that. Let's suppose that we have f of xy, so z is equal to f of xy. It's differentiable at a point p naught, and the gradient of f at p naught, let's suppose that that's not the zero vector. Just because the zero vector is orthogonal to everything, if it's not the zero vector and it's orthogonal to another non-zero vector, that's going to mean that it's orthogonal in the sense of perpendicular. Okay. All right, so let's suppose I took a look at a level curve, f of xy is equal to k. Okay. Now I'm going to just suppose that my level curve can be smoothly parametrized, which means I could get an arc length parametrization for it. So R of S is my arc length parametrization for the level curve. Okay, now it's certainly possible to have a level curve that cannot be smoothly parametrized. So this doesn't cover all cases. I'm just taking a look at the nice case. Let's suppose that our level curve can be smoothly parametrized, and let's take a look at that. Now what's nice about that is, remember, if I use an arc length parametrization, I know that the magnitude of the derivative is 1. Okay, so that I'm never getting a zero vector here. Okay, all right. Well, if I were to apply my function to points on this level curve, with directional derivatives, we were restricting the domain of the function to be lines that went in a particular direction. Now, I'm not assuming that my level curve is a line, but I've been able to parameterize it. I am supposing that. Okay, and I'm going to restrict the domain of my function to being on that level curve. Well, then I know that f of r of s is just k. If I plug in points on the curve, the whole definition of the curve is that when I plug in those points, I get this constant k. Now that means that the derivative with respect to s of f of r of s would equal 0. Okay, so let's take a look. Z is a function of x and y. If I'm restricting it to points that are on this curve, I've described those points in terms of s. So we're basically saying that this 0 here, that's the derivative of z with respect to s. Because I plug in s, I get a point on this curve, I plug that into f, and that gives me k, because I'm restricting to points that are on that level curve. Okay. But I can work out then what this derivative is. So I know that 0 is equal to dz by ds, but according to chain rule, that would be partial x, partial s, x prime of s, partial z, partial y, y prime of s, whoops, y prime of s, multiply the derivatives on the paths, and add them together. So that's partial z, partial s, x prime of s, plus partial z, partial s, y prime of s. And as we've seen, that's a dot product. That's partial z, partial s, partial, I'm sorry, I wrote s there. That should be an x, and that should be a y. I apologize. On my diagram, where I should have had del z by del x, I'd initially written an s. And then when I was copying off the diagram, I wrote both of these as s's, when this should be an x here and this should be a y. Okay. So we're getting partial z, partial x, comma, partial z, partial y, dotted with x prime of s, comma, y prime of s. But that's just the gradient of f dotted with r prime of s. And if we're saying that that's 0, we're saying that the gradient is orthogonal to the derivative of my level curve. And if we've supposed that at P naught, the gradient is not zero, I know this first factor isn't zero. We supposed we had an arc length parameterization, so I know this second factor isn't zero because it's a unit vector. So that means that they're actually perpendicular. And what we could say is that if the gradient of f at p naught, if I have a differentiable function and the gradient of f at p naught is not zero, then it's going to be normal to the level curve. So if the gradient of f at p naught is not zero, it is normal to the level curve, meaning it's perpendicular to the line that's tangent to that curve. Now, this applies to functions of two variables. I could modify the argument, and you'll see this in your textbook, if I had a function of three variables. If I have a function of three variables, we're talking about some sort of a surface. Here's a lovely surface. Pretend it's hollow, okay? Now, if there's a point here, there are going to be infinitely many curves that pass through that point, okay? So, and I was applying this to curves. But what we could modify this argument quite easily to say that the gradient of f at this point would be normal to every single curve that passed, every single curve that passed through this point, yes. And this would be a level surface that I had for my function. Okay. And if it's going to be normal to every curve on the surface, it's actually going to be normal to the surface. So what happens is for a function of two variables, differentiable functions, for a function of two variables, the gradient's going to be normal to the level curve. For a function of three variables, the gradient is going to be normal to the level surface. Okay, so if I have g of x, y, z equals w, differentiable at p naught, if the gradient of g at p naught is not zero, it is normal to the level surface that contains p naught. Pretty cool. We'll take a look at how we can take advantage of that in the next video.